Hello students, welcome back to the Relational Model session of Database Management Systems. In this session we will learn the Relational Data Model, structure of relational databases, database schema, keys, schema diagrams, relational query languages, the relational algebra. The relational data model is most practiced data model in the commercial data processing applications, such as MS SQL Server, Oracle, MS Access, MySQL, etc. Because of its simplicity, it eases the job of the programmer. A relational database consists of a collection of tables, each of which is assigned a unique name. You can observe in the below example that each table is assigned a name. A row in a table represents a relationship among a set of values. In the relational model, the term relation is used to refer to a table. The term tuple is used to refer to a row. Similarly, the term attribute refers to a column of a table. Relation instance refers to a specific instance of a relation, that is, table containing a specific set of rows at any given moment. A set of permitted values are called the domain of that attribute. For example, any number with maximum 10 digits length can be stored in account number column of any row. So set of numbers from 0 to 9,999,999,999 is the domain of account number. Similarly, branch name column can have any name with maximum of 15 characters. Any combination of characters including small letters, capital letters, special characters and digits 0 to 9, with length of 0 to maximum 15 can be stored in branch name. Similarly, any number with maximum of 13 digits and 2 decimals can be stored in the balance column. A row of the table can be derived from the combination of these domains. So cross product of all these domains is set of all possible rows in a table. Mathematically, a relation is a subset of Cartesian product of a list of domains. That is why we use the term relation to indicate a table. Attributes can be composite or atomic. Attributes such as address, name, etc. can be subdivided further as below. Address is having multiple subparts: house name, house number, cross number, area name, city, state, country, pin code, etc. Name can have subparts: first name, middle name, last name. Even date can be subdivided as day, month, year. All these are composite attributes. A domain is atomic if elements of the domain are considered to be indivisible units. For example, account number, balance, employee ID, city, pin code, etc. The null value is a special value that signifies that the value is unknown or does not exist. For example, consider instructor relation. Each and every instructor will be issued an ID, every person will have name, an instructor must be associated with a department. And he will be getting salary, so all the first 4 attributes cannot be left without values. But consider attribute phone number. Even if everybody will have phone numbers, some people may choose to live without phone number. Or the instructor does not wish to share his phone number. Null is not equal to 0, blank space or any other values in the database. Database schema is the logical design of the database. Database schema refers to overall database design, relations and their attribute names, rules for storing data in them, relationship among different relations, etc. You can observe in the example that schema of instructor relation contains the rules for the data to be stored in each attribute and also the list of attributes. Database schema may include more information than the one in the example. However, the example gives overview and limited to a relation. The database instance is a snapshot of the data in the database at a given instant of time. Collection of all tables along with data in it refers to database instance. For better understanding, let us compare database with programming language concepts. The concept of a relation corresponds to the variable of a programming language. Then the concept of a relation schema corresponds to the type definition of programming language. In general, a relation schema consists of a list of attributes and their corresponding domains. The concept of a relation instance corresponds to the value in the variable of programming language. The value of a given variable may change with time. Similarly, the contents of a relation instance may change with time as the relation is updated. In contrast, the schema of a relation does not generally change. No two tuples in a relation are allowed to have exactly the same value for all attributes. Keys provides a way to specify how tuples within a given relation are distinguished. This is expressed in terms of their attributes. That is, the values of the attribute values of a tuple must be such that they can uniquely identify the tuple. A superkey is a set of one or more attributes that allow us to uniquely identify a tuple in the relation. In simple words, values in the superkey attributes collectively do not repeat. Consider the instructor relation. The ID attribute is sufficient to distinguish one instructor tuple from another, as no two instructors can have the same ID. Thus, ID is a superkey. On the other hand, the name attribute of instructor is not a superkey, because several instructors might have the same name. Similarly, there may be multiple instructors in each department, hence, the department name may also repeat. And multiple instructors may be getting the same salary. So, name, department name, and salary attributes cannot be superkeys. Hence, ID is the only superkey in relation instructor. Formally, let R denote the set of attributes in the schema of relation R. We say that a subset K of R is a superkey for R. If T1 and T2 are in R, and T1 is not equal to T2, then T1.K not equal to T2.K. A superkey may contain extraneous attributes. For example, the combination of ID and name is a superkey for the relation instructor. That means, if all values in ID attribute are unique, then values of ID with name combinations are also unique. If K is a superkey, then any superset of K is also superkey. Candidate key is a superkey with minimal set of attributes. It is possible that several distinct sets of attributes could serve as a candidate key. Suppose there is only one person with any name in any of the address. Then we can take set of name and address as candidate key. Observe in the example that name, Murthy, is repeated but when combined with the address, will be unique. Primary key is the term used by database languages to denote a candidate key. Account number attribute in account relation, ID attribute in instructor relation, and department name column in department are examples of primary keys. The database designer chooses a candidate key to identify tuples within a relation. This candidate key is the principal means of identifying tuples within a relation and is termed as primary key in database languages. A key, whether it is primary key, candidate key, or superkey, is a property of the entire relation, rather than of the property of individual tuples. Any two individual tuples in the relation are prohibited from having the same value on the key attributes at the same time. The designation of a key represents a constraint in the real-world enterprise being modeled. Hence, primary keys are also referred to as primary key constraints. Foreign key. Consider the instructor and department. Each instructor will be working under a department of the institution. What happens if an instructor exists with department name that is not existing in the institution? That does not give meaning. Therefore, we need to restrict instructors by department name that is listed in the department table. Each update in the instructor table must be validated by cross-checking with the department table to ensure the existence of the department name. All the departments of the institution are listed in the department table, and each department details appear once in the department relation. Hence, The department name in the department table is primary key. A foreign key constraint from attribute A of relation R1 to the primary key B of relation R2 states that on any database instance, the value of A for each tuple in R1 must also be the value of B for some tuple in R2. Attribute set A is called a foreign key from R1, referencing R2. The relation R1 is also called the referencing relation of the foreign key constraint, and R2 is called the referenced relation. Schema diagrams. Schema diagrams graphically represent the overall database design. It depicts relations, their attributes, primary keys, and foreign keys in the database. Each relation appears as a box, with the relation name at the top in blue shaded box, and the attributes listed inside the box. Primary key attributes are shown underlined. Foreign key constraints appear as arrows from the foreign key attributes of the referencing relation to the primary key of the referenced relation. We use a two-headed arrow, instead of a single-headed arrow, to indicate a referential integrity constraint that is not a foreign key constraint. The example in the image contains schema diagram for the university database. We use the same database to practice SQL queries in the next chapters. Relational query languages. A query language is a language in which a user requests information from the database. These languages are usually on a level higher than that of a standard programming language. Query languages can be categorized as imperative, functional, or declarative. In an imperative query language, the user instructs the system to perform a specific sequence of operations on the database to compute the desired result. Such languages usually have a notion of state variables, which are updated in the course of the computation. PL/SQL is an example of imperative query language. In a functional query language, the computation is expressed as the evaluation of functions that may operate on data in the database or on the results of other functions. Functions are side effect free, and they do not update the program state. The relational algebra is a functional query language. The relational algebra forms the theoretical basis of the SQL query language. Practically used query languages, such as the SQL query language, include elements of the imperative, functional, and declarative approaches. In a declarative query language, the user describes the desired information without giving a specific sequence of steps or function calls for obtaining that information. The desired information is typically described using some form of mathematical logic. It is the job of the database system to figure out how to obtain the desired information. The tuple relational calculus and domain relational calculus are examples of declarative query languages. Queries are written to get data from the database in a desired manner. The relational algebra consists of a set of operations that take one or two relations as input and produce a new relation as their result. Fundamental relational algebra operations are unary operations, select, project, and rename, binary operations, union, Cartesian product, and set difference. Although the relational algebra operations form the basis for the widely used SQL query language, database systems do not allow users to write queries in relational algebra. There are some online practice tools for students learning, similar to the one shown in the image. Students should be aware that database management systems follow mathematical rules. Note that a relation is a set of tuples. Sets cannot contain duplicates, so relations cannot contain duplicate tuples. However, tables in database systems are permitted to contain duplicates unless a specific constraint, such as a primary key, prohibits it. While discussing the formal relational algebra, duplicates are eliminated, as this is a requirement of the mathematical definition of a set. Multisets are sets that can contain duplicates. Relational algebra can be extended to work on multisets. Now we will see relational algebra operations one by one. Select operation. The select operation selects tuples that satisfy a given predicate. A predicate contains expressions that select only the desired tuples. We use the lowercase Greek letter sigma to denote selection. The predicate appears as a subscript to sigma. The argument relation is in parentheses after the sigma. Consider some examples. Select those tuples from instructor relation where instructor is getting more than 35,000 salary. Sigma, salary greater than 35,000, from instructor. This results in retrieving tuples from instructor relation with salary more than 35,000. One more example. Select those tuples from instructor relation where instructor is working in physics department. Sigma, department name equals physics, from instructor. This results in retrieving tuples from instructor relation with instructor working in physics department. Combination of predicates. We can combine several predicates into a larger predicate by using the connectives and, or, and not. To retrieve instructors from physics department, and also with more than 35,000 salary from instructor relation. Following is the query. Sigma, department name equals physics, and salary greater than 35,000, from instructor. This will result in tuples satisfying both conditions. To retrieve instructors, either they are from physics department, or they are getting more than 35,000 salary from instructor relation. Following is the query. Sigma, department name equals physics, or salary greater than 35,000, from instructor. This will result in tuples satisfying either of the conditions. Next relational algebra operation is the project operation. Using project operation, desired attributes or columns of a relation can be retrieved in the output. Projection is denoted by the uppercase Greek letter pi. The general form of project operation is as below. Pi, subscript attributes list from relation. Expressions can also be used in the columns list. For example, pi, name comma salary from instructor. This relational algebra expression gives output with two columns name and salary as below. We can also retrieve annual salary from existing salary attribute using project operation as pi, name comma salary multiplied by 12 from instructor. This relational algebra expression gives output with two columns name and salary multiplied by 12 as below. Composition of relational algebra operations. Select and project. Consider retrieving the name and salary attributes from the instructor relation, where the department name is chemistry. To select particular attributes in the output, we need to execute the project operation. And to select particular tuples that match the department name, chemistry, we need to execute the select operation. So, this requires executing two relational algebra operations, select as well as project. An important fact is that both the input and output of a relational algebra operation are relations. So, we can feed the output of one operation to another operation to get the desired result. If we execute project operation first, then the result relation does not contain department name attribute that is required by predicate of select operation. Hence, we execute select operation first, then we feed output of select operation to input of project operation. So first we execute relational algebra query, select department name equals chemistry from instructor. Then we execute relational algebra query, project, name comma salary from output of previous query. Final query is project, name comma salary from, select department name equals chemistry from instructor. The Cartesian product operation. The Cartesian product is denoted by a cross symbol. The Cartesian product of two sets combines each element of one set with each element of another set. As shown in the example. In the Cartesian product of set A with set B, each element of set A is combined with each element of set B. Similarly, the Cartesian product operation, in relational algebra, combines tuples into relations. Each tuple of the first relation is combined with each element of the second relation, as shown in the example. And we write the relational algebra operation as A cross B. You can observe in the relation, instructor cross department, that the attribute, department name, is repeated 2 times. One is from the instructor relation and the other is from the department relation. We may require a mechanism to identify both attributes separately, so we qualify attributes in the Cartesian product with their relation name using the dot operator, as shown in the example. Some may choose to qualify only those attributes which has the same name in each relation, as shown in the example. Some information can be derived from combining 2 relevant relations in a meaningful way. In instructor and department relations, department name is a common attribute. We can join 2 relations using this attribute. Tuples having the same department name in the Cartesian product can be considered. The relational algebra operation for this is sigma instructor dot department name equals department dot department name from instructor cross department. The resulting relation of this operation has fewer tuples than the original Cartesian product and is more meaningful. Such an operation is called the joining of 2 tables. It is denoted by a cross symbol closed at both ends. Relational algebra operation for the above can also be written using the join symbol. Instructor, join, instructor dot department name equals department dot department name, department. Relations in the database have names. The results of relational algebra expressions are also relations, but they do not have a name. It will be useful in some cases to assign names for results of relational algebra expressions. We can rename the results of relational algebra expressions with the help of rename operator. Rename operator is denoted by the lowercase Greek letter rho. If E is the relational algebra operation, then rho x of E is the relational algebra expression for rename, where x is the name given to result of relational algebra expression E. For example, rho seniors from sigma salary greater than 35,000 from instructor. Resultant relation of select operation is assigned name seniors. Union, set difference are basic relational algebra operations, and we can derive set intersection using set difference. Set operations can be executed on sets with similar elements. Set operations on sets with different types of elements is not permitted in mathematics. For example, union of instructor names and budget in department relation cannot be done as they are of different domains. Databases also do not allow set operations on tuples with different domains. Union of instructor names and parent names gives meaning as both are names of persons, and both are of character data type. Tuples are elements in a relation, and when executing set operations on relations, tuples in both the relations must be of same domain. So, we use project operation to choose attributes with common domains in both the relations before executing set operations. To get union of instructor names and parent names, we can write following expression. Project, name from, instructor, union, project, name from, parent. This expression will retrieve persons' names who are either instructors or parents. Set difference is denoted by minus symbol. Set difference returns elements of first set that are not in second set. It is possible that some of the instructor's children may be studying in the same institute, hence their name appears in both relations. To find the instructors whose children are not studying in the institute, we can execute set difference expression. Expression for this is project, name from, instructor, minus, project, name from, parent. Out of 5 instructors Einstein and Murthy are there in parents relation also, hence 3 instructors' names excluding Einstein and Murthy are in the output. Similarly, set intersection operation gives elements of sets that are in both sets. Retrieve instructors whose children are studying in the institute. Intersection of instructor names and parents' names will do this. Expression for this is project, name from, instructor, intersect, project, p. Name from, parent. In the example, Einstein and Murthy are in both instructor and parents relations. Hence set intersection gives 2 elements, Einstein and Murthy. The assignment operation, denoted by left arrow, works like assignment in a programming language. The assignment operation allows to write a relational algebra expression by assigning parts of it to temporary relation variables. For relational algebra queries, assignment must always be made to a temporary relation variable. Assignments to permanent relations constitute a database modification. In the example, output of the select operation is assigned to a temporary relation temp_instructor. This completes the session on relational model. Thanks for watching. Please subscribe to the channel to keep updated. In the upcoming sessions we will learn structured query language, entity relationship model, relational database design, and transaction manager. If you have not watched the introduction class of database management systems, please watch it in the given link.